tutorial. So first example, I thought that might be useful for you to get familiar with these equations is to write BP equations, so the belief propagation equations for circular coloring. So was that problem? That's similar to graph coloring, except that when in graph coloring, every edge can take any pair of colors as long as they are not the same. In circle coloring, you still have Q colors, and you arrange them on a cycle. And then the rule is that a given color S can have neighbors that have color S plus 1 or S minus 1. But not the others. Okay, so these little edges, so this would be somehow graph, not the original graph, but graph on the color indices. And the edges are telling you who is allowed to be neighbor to who. And so this would be the circular coloring, and in this representation, the normal coloring would be, okay, I said I have 6 colors here. So I would not, this would not be allowed, no self loops, because given color cannot be next to each other, but otherwise it would be a complete graph, right? So, boom, 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 and boom, 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 like everybody can be next to everybody, but in the circular coloring, I can be only next to my neighbors on that circle. So it's also a constraint satisfaction problem on graphs, it will have its, similar properties. And what I'm just to get familiar with the belief propagation equation, just try to write them for this problem instead of this one. So that's the first thing. 1 and 2. So that's something that is useful in some of the computations, that not in any of those that I am doing in the lecture, but in general, that when we wrote the bette free energy as a function of all the messages, and you can be specific to coloring. It's true in general, but let's make it specific to coloring. So it's a function of all these messages for all S and for all ij. And actually, the belief propagation equations are stationary points of that function. And so that's something you can try to prove. So I wrote the expression for this bette free energy, and the assignment would be show that the BP equations are stationary points. So, make a derivative of this expression with respect to each of the messages, set it to 0, and show that if this needs satisfied, that's satisfied if and only if the BP equations are satisfied. Right, that's what I mean by stationary point. I mean, it's either minimum, maximum, or a saddle of this function, the fixed point of the BP equations. So that's kind of an exercise with manipulating these equations and seeing, how things work out. Okay. So now I should let it here. So then maybe, okay, let's see how I can manage with the blackboard. So what I just reminded on the blackboard, these somehow 2 axes that we had yesterday, what we learned so far about the random graph coloring is BP equations, the expression, I didn't explicit the Zi, Z, and J, but I already wrote it at least twice, the expression for the bette entropy. And our conclusion from yesterday that we will start with today to actually conclude this story about the relation between the random graph coloring and the planted coloring, where in the planted coloring we create still some kind of a random graph, but from a different ensemble. We first choose a configuration S star, and then we choose the graph at random such that the S star is a valid coloring of that graph. And yesterday, we said that this ensemble has 2 very interesting properties. First of all, as long as the annealed and quenched entropies are equal, then this planted ensemble is exactly generating random graphs. And so now we will be working, we will be assuming that this is true, because somewhere at very low degree this is true. That's somehow what, our computations so far were suggesting that this is true. And now we will basically see what's the first place where something gets wrong, where we have some like paradox. And that will, things, if it is true for a while, then as long as the free energy is analytic, so as long as we don't have any phase transition, it must stay true, because the free energy is analytic until the first phase transition that is encountered, right? So the first place where this breaks will be the first phase transition that we encounter on that axis. So that's what we will be going after, basically working under this assumption and trying to see what's the first place where we just have something non-consistent. And the second property that we will be using, that not only the two ensembles are the same, but also this planted configuration acts as an equilibrated configuration on the graph. Okay, and yesterday we were mentioning this, these definitions of what are thermodynamic states or Gibbs states, and you were saying that the way to check if something is a nice thermodynamic state is to draw a random configuration from it, and then see if that configuration is, is somehow, if you put it on a boundary of your system, if it is inducing the same probability distribution as you started with. So this translated to the planted coloring and, to something like belief propagation. So how will we test something like that using belief propagation, or using, what's another somehow way physicists have in their or in our baggage to equilibrate and describe probability measures? That's Monte Carlo, right? We could write Monte Carlo that has detailed balance with respect to our Hamiltonian and just equilibrate and see where we are going. So we will be doing the following, experiment. Or not experiment in physics. It's interesting because in math, any kind of a numerical investigation, people call it experiment. Of course, in physics, we call that simulation. So say simulation. So that will be the following thing. So we generate a graph in this planted way. And then, so we do in parallel, if it's useful to compare BP with Monte Carlo. So we do in parallel two things. So what we do, so let's do the following simulation. So initialize, so first generate graph in the planted way with a given S star, etc. Then initialize BP, so belief propagation, in S star. So by that I mean that, this message chi-s from I to j will be equal to a delta function on S star I. Okay? So I could also put the I here. I. So this Q component vector that goes from I to j, where these are the components, will be 0 if the component is not S star and will be 1 if the component is S star. So that's what I mean, like initialize BP in the S star. You just initialize it as, these where we interpreted those as probabilities that I takes this color if the edge between I and j is absent. And now we are just setting this probability equal to 1 if Si is equal to Si star and 0 otherwise. So this means that we are somehow starting the belief propagation as if this was the only configuration there is. Okay? Initialize BP, iterate. And see, and okay, iterate. And then, compute. Correlation between, I say it in words, between S star and the fixed point. So so this would be, okay, just to make it clear, initialize, that means at time equals 0, this will be this. And then we compute the correlation between S star and chi which means that we will compute the sum over I, 1 over n, chi I to j at the fixed point, and each of them will be evaluated in the SI star. Okay, so this, if for instance at the end, okay, let me also normalize in this way, the Florent did yesterday similarly. So if at the end we went back to this fixed point 1 over q everywhere, this would be 0. There's no correlation between that fixed point and the SI star. If, for instance, this would be a fixed point, then this is just 1 minus this would be just 1, right? So if we didn't move at all from the S star, this correlation, I will call it capital Q as overlap, will be 1. And if we went back to this paramagnetic fixed point, then it will be 0. So we will see where we are, if we are at 1, at 0, or somewhere in between. So that's the first simulation. And in parallel, we can run a similar thing. We initialize Monte Carlo Markov chain in S star. Well, that's easy. You just, initializing Monte Carlo, that's just the first configuration in which you are starting, and then you iterate, equilibrate. And compute correlation with the S star in the same way. So in Monte Carlo, you don't have any xi, but you have the configuration after the equilibration, and you just compute in how many elements it agrees with the S star. Right? So you also, this way you compute the correlation. Okay, so we do that. So what do you think it will get? In terms of our pictures. Let's see with this one, right? Like first thing that you should, if you remember from yesterday, at some point we were computing on this tree where we fixed the boundary far away. We were computing the probability that this faraway boundary is implying the root. Right? And for instance, when we were computing this, well, this was somehow an upper bound on the fact that this experiment will actually lead to something non-trivial. Right? These things are related because the configuration S star here plays the role of this fixed boundary from which we are then iterating the belief propagation and seeing where is the fixed point. And when you think of the Monte Carlo, one is maybe more familiar with that. What are we doing here with the Monte Carlo? So you have your system, and you initialize Monte Carlo in S star, which is an equilibrium configuration in your system, right? And then you run your Monte Carlo, and you measure what is at the end the correlation with your initial condition. So say that you do this in Ising ferromagnet on a lattice, for instance, why not? Then if you're in the ferromagnetic state, your correlation will be exactly the magnetization. And if you're in the paramagnetic state, your correlation will be 0. Right? When I say equilibrate, okay, I should precise. Equilibrate, I should say that the time for which you run it is very large, but it's you just run a very large number of sweeps, not so the number of sweeps you run is some large constant times n. Constant C I already used, big K, where K is something large. It's not something exponentially large in n. Because exponentially large in n, first of all, you cannot do that in practice, right? Unless your system is ridiculously small. And if it is exponentially large in n, well, then with Monte Carlo, you're just always sampling uniformly your Boltzmann measure. So for instance, even in the ferromagnetic phase of the Ising model, you would just be half of the time in the plus state and half of the time in the minus state. So overall, your magnetization would be 0, and you would not really see the difference between the paramagnet and the ferromagnet if you were running it for this long, right? You will only see the difference if you run it for long, but say linearly long, or maybe quadratically, or we could argue like that, but there is some polynomial. But say that it's linearly long. Okay, so thinking about that example with the Ising model, and thinking that here the paramagnet also plays some role. But so if we go back to the paramagnet, that means that the Monte Carlo just converges somewhere, run somewhere away from the S star as a random configuration would be. well, then this means that basically it's paramagnetic. Like we went away from the initial condition, means that there are no like really correlations with the initial condition. But if we stayed close to it, well, then it means that we are in a well-defined thermodynamic state, and the Monte Carlo would be sampling that state. Right? That is somehow that is correlated with the initial configuration. But note that here the initial condition is not like or +1 or -1, it's something random because we chose it random. So, okay, so that's somehow what we should imagine. So let me show you now just some picture of this is data. I actually have done this experiment. So this would be for coloring with 5 colors. Ignore for a moment this notation. This just means that that's the coloring problem. On a graph that is rather big, so 100,000 nodes. It's not ridiculously small. And now this is the average degree. And the y-axis is this overlap, this capital Q that I wrote here, okay? And I actually run it. So the green curve, that's the planted initialization. So I initialize the belief propagation in the S star. And the blue curve, the blue curve is initialized randomly. So I will get back to it in 20 minutes or so. So let's stick to the green curve. So we see that up to some degree, we go back to the paramagnet, but starting from here, we don't go back to the paramagnet. So what does it mean? How do we interpret it? We stay, and we see that the correlation is rather big, 0.8. It discontinuously jumps to some correlation magnetization, think of it similarly, magnetization towards the planted configuration in essence. So you stay kind of really close to it. You only, as you're say running, and I should say this is the result of the BP. If you ran the Monte Carlo, you will just find the same points, okay? They will be a little bit more noisy because Monte Carlo is a little bit more noisy, has a bit more finite size effects than the belief propagation. But if you do it carefully, average over instances, etc., you will just find the same curve. So this is kind of reassuring for us as physicists because we are kind of familiar with the Monte Carlo. So that somehow makes us trust also the belief propagation that it's giving us something meaningful. It's reassuring. I mean, if we understand properly, if we thought about the math a lot, then, we would be happy with the belief propagation anyway. But if we didn't yet, this is good to see that these two agree. So what does it mean? So what else can we do? So, I mean, I told you only one hammer, right? So let's use our hammer. So we already used this, we used the belief propagation. So let's use this, let's look what's the bette entropy that corresponds to the fixed point that you reached. Right? So more precisely, okay, let me erase the homework. Hopefully everybody noted it now. So the next curve I will show you in the figure is the, and now the way, so is the S bette of, whatever is the fixed point from here. So the fixed point of whatever we reached when we did this experiment, minus the annual entropy. Oh, is it this way? Yes. So okay, I think it would be more meaningful to flip the sign, but okay, I had this picture in this way, didn't change it this morning. So this is how it looks like. Okay, so here is the logarithm of the z planted minus the logarithm of the z random. Well, that's the annual entropy. Because this paramagnetic fixed point, that's what we derived yesterday, that it gives a bette entropy that is exactly equal to the annual entropy. And the logarithm of planted, that's what I call there, this S bette of, okay, planted fixed point I could write here. So what do we see? So first of all, we have this region. Like when something interesting starts to happening, this thing is negative. This thing. So at first, so now let us, okay, we should draw our axis. So, but I call my, okay, let's stick to the notation in that figure. So I define this CD, this C, and CS. So 3 somehow points. This one is when this non-trivial fixed point appears. This one is when this difference between free energies becomes positive, and this one is when this paramagnetic fixed point disappears. So I will postpone explanation of this one 15 more minutes. But let's see first, so what's happening here? Okay, here everything is fine, right? We just consistently find this paramagnetic fixed point, and there is nothing that would be telling us that anything is wrong with this Sn yield equal S quenched, and that anything is wrong with saying that the model is paramagnetic and nothing particular is happening. So that's indeed what is happening. So here is just paramagnetic. So here, the thermodynamics of the model is a paramagnet, as much as you can imagine it. There is nothing wrong happening here. Now what happens here between CD and CC? So notably this N yield entropy is bigger than the planted one. And I said, so this is indeed estimating the entropy of the state that the belief propagation on the Monte Carlo are describing. So the most natural explanation is that indeed the whole entropy of the system is still equal to this Sn yield. But it actually splits into many parts this big. And we remember that entropies are defined as logarithms of something exponentially big. So if the difference of entropies is some finite number, it means how many of these states, how many of these blobs they are, right? The entropy of those blobs would be the difference, the Sn yield minus S planted. I will call it capital sigma. So that would be the entropy of how many of these states we have there. And it's some positive number. But since it is again the entropy, it means that there are exponentially many of them. So you're seeing here we are in a very different situation than in the Ising ferromagnet where we have two states. And here, with Q colors, we could somehow think maybe we have Q factorial. But nothing like that. We have exponentially many in N of them. Right? That's a very different kind of beast in terms of a phase transition. Right? And this, okay, so in physics of glasses, this phase, and this is called complexity in the cavity method. It has nothing to do with computation complexity. It's a bit of an unfortunate word that I don't like so much. In the physics of structural glasses, this is called the structural entropy. And this describes how many states there are in the glass. And this phase where the structural entropy is positive, it's called the dynamical one-step replica symmetry breaking phase. Okay, that's a horrible name. But just, for those of you that heard about this replica symmetry breaking, maybe to make a connection, or whatever. I don't want to talk about even why there's some replica symmetry breaking, how that's related. So that's what's happening here. So I will also do, I don't need this. And with this picture, I like to somehow do this cartoon of how the space of all the colorings looks like. So in a paramagnet, you can go from everywhere to anywhere. And so somehow if this is the phase space, this blob somehow represents all the valid colorings, and they somehow all, you can walk from one to another. It's somehow a connected blob. Whereas here, I said you have exponentially many of them, and they have, so we somehow represent it by this. And we say that each of them is a cluster. There are clusters of colorings. And there are, so I cannot draw exponentially many, but there are many. And they are somehow all of the same size. All of them have this entropy. And then there are some small ones, and there are also some big ones, but they don't matter for equilibrium. They would, if you were interested in large deviations, they would matter. But if you are interested in equilibrium, all of them have the same size. So that's interesting. So you see, for instance, some comments on what's happening at this transition. So this is, in glasses, this is called the dynamical glass transition. Should I do it now? Okay, maybe let me do it now. Let me do, one more picture with this CD here and CC here. But now, let's imagine that we would not be studying our problem at 0 temperature as we do for the coloring, but that we would just put temperature. We would put some, the configuration that have monochromatic edges would not be completely forbidden. They would just have some penalty, and the temperature describes the penalty. Then these phase transitions would actually extend into phase transition lines. This would be TD. This would be T. Okay, I will get to this one. So this would be TD. And what would be the important thing happening at this TD? So, do I need that? Maybe we could pull it up so that I can use the rest of the blackboard, or I erase this. Yeah, let's pull it up. I will not be needing it for a while. Okay. So what will happen at this, so here we are paramagnetic. So how do we, what to do to locate this dynamical temperature? Well, that has a very easy, they have a very, very natural dynamical interpretation. Run your Monte Carlo and see what's the equilibration time in your Monte Carlo. Okay, so just empirically, compute the correlation with the initial condition and see when it plateaus. So as you're approaching this dynamical temperature, the way the correlation in the MC time will look like some kind of a correlation with initial condition. So when you're at very high temperature, the correlation just decreases really fast and then it is 0, right? When you're somewhere at high temperature, you equilibrate real fast, okay? And when you're lowering the temperature and going closer to the line, well, it's becoming a bit slower. All right, but what's happening here actually is that you start to see a kind of a plateau, and you have this type of a relaxation. And then as you're getting really, really close to this TD, and as you approach it really, you just stay on the plateau. So that's what's happening. If you measure this kind of a figure, that's the way to locate numerically this TD in pretty much any kind of system, and that's what people do when they study structural classes. Okay. So this phase transition that you have here in the graph coloring, the CD, is really reminiscent of this dynamical glass temperature that people talk about when they study structural classes, and notably, it would be exactly correspond to it in the mean field moles of structural classes. And the corresponding theory that people developed in physics is the random first order phase transition theory due to people like Volines, Kirkpatrick, Drumalai, something like 40 years ago. So what's happening in the random graph coloring is exactly that. So that's about this CD and about then this phase where we have exponentially many Gibbs states or clusters of colorings if you want. Now, what happens here at CC? So how did we define CC? That was when the structural entropy went to 0. That's the definition of CC, right? What would it mean that beyond here, that the entropy of the planted state is bigger than the whole entropy? This just cannot be, right? I mean, the SN yield is an upper bound rigorously on the whole entropy. It cannot be bigger. That's just by trivial Markov inequality. So the planted cluster cannot be bigger than the whole. So that's a paradox, right? And in classes, this is called the Kautzmann paradox. When the structural entropy goes to 0, that's called the Kautzmann paradox or the Kautzmann temperature that corresponds to what people call the ideal glass transition in physics of glasses. Here in random graph coloring, it is the same thing, something like really different happens at this CC. But in terms of our interpretation with the planted coloring, it just cannot make sense anymore. Because, our calculation of the entropy of the planted cluster is correct, and it just cannot be bigger than the annual entropy. So what can go wrong? It must be that some of our assumptions went wrong. And what goes wrong, we didn't assume many things, we only assumed this. So at CC, this just cannot be true anymore. Beyond so we call C like for condensation, beyond this critical degree of condensation, it cannot be that the annual entropy is equal to quenched entropy, because if it was true, then the planted ensemble would have to be equivalent to the random ensemble, but the entropy of the planted cluster is bigger than the annual entropy, so this just cannot be. And since it is the only thing that we assumed, it must break here. Well, this is not a proof that it breaks here, because it could also break before, but this, okay. In physics, we can work under the self-consistency. Unless we find something wrong with our assumptions, we assume that they are correct, okay? So this is not proof mathematically, but here, it must get wrong, because we just cannot think of how to put it together consistently. And that's indeed what happens. So at this C condensation, this fails. So this is the true phase transition, in the sense that the entropy, or if you want free energy, if you are working with this temperature, gets non-analytic. Because up to this point, down to here, the annual free energy, which is easy to compute, that's just this computation we did in the first half an hour of the first lecture, is equal to the actual quenched free energy. But starting from this point, it is not. So that's what happens here. And then this phase from here on, that's called the static RSB. And to continue my drawing, so then there would be somewhere here, there will be the colorability threshold, which, this description is not telling us how to compute. So what happens physically is that we will still have this many clusters, but actually, there would still be exponentially many of them if we count all of them. But if we count those that matter for the total entropy, there will be only few of them. And how many of them, that's actually a random variable that is distributed as some Poisson-Dirichlet distribution for, reasons that I could explain, but maybe that's not the most important thing to explain. But there is only typically, say, 5 or 3 or 20 of them that matter to describe what's happening at equilibrium. And this number actually is a random variable. It's not a so what's happening in this region, the striking properties of this region is that many quantities that we would somehow think are self-averaging in physics in general are not self-averaging in this region. Like, for instance, so when people talk about spin glasses, they would talk about this Edwards-Anderson overlap, which would be overlap between two configurations taken at equilibrium. And if we have, say, two states that dominate, and we just happen to take one configuration from here and one configuration from here, they will be basically uncorrelated. But if we hit the same state twice, then they will be correlated. So the distribution of these correlations is non-trivial. It has, at least 2 delta peaks. It's not 1 delta peak, as it would be in most physical systems where we expect things like correlations and magnetization, etc., are self-averaging. If you take a system big enough, it doesn't matter on the realization of which configurations we picked. The correlation between them will be the same number all the time. So that's what happens here. And eventually all these clusters disappear, and that phase space is empty, and that marks the colorability threshold. So that's this. Then to describe more in detail this phase, since we don't have the equivalence with the planted ensemble anymore, we really need to go into this methodology where we really describe fixed points of BP. Each fixed point corresponds to one cluster, and then we do statistical physics over these fixed points. Then we can compute large deviation functions of these clusters and many things. Okay, but I won't be going into that. That would take a few more lectures. Yes? What does the size? The size of the circle mean is the size is proportional to the entropy of the state. So that just means that there are more configurations if say you were running the Monte Carlo, then what you are doing, you are basically uniformly sampling the configurations that belong to that circle. Yeah, and if the circle is bigger, then it means that you're uniformly sampling over bigger space.
So who is a bette coloring?
Okay, so each, I always say each pixel in this figure is one assignment of colors. And then, the shaded pixel is a valid coloring. So many of them, are valid colorings. And then this picture somehow corresponds, the distance in that picture, that would be the Hamming, what people call Hamming distance between the strings. That means the number of nodes on which they differ. So, for instance, being in one cluster would mean, roughly, that if you're flipping one spin while staying a valid coloring, you can walk from one coloring to another. And if you cannot walk from one another, then it means that you're in a different circle. That, these are ergodicity. All this is for one graph, yes. I said at some point that, for the purpose of some computations, I will be averaging over graphs, but mostly I'm thinking, fixing the graph once or forever, and thinking how does the measure over all the possible colorings looks like. So that's how it looks like. And it's related to this. Now I can write this is the Gaussman temperature. So this condensation is related to the ideal glass temperature, or sometimes called Gaussman temperature. So,
all colorings are allowed. So, because there's no.
Yes, but.
So then you wouldn't have any of these.
You do. That's what this line means. That it's a good point. That, for instance, the C colorable, that doesn't have any meaningful continuation in temperature, right? This doesn't mean anything. You can decide at 0 temperature if the ground state has 0 energy or not, but at finite temperature, there is some ground state energy, but this doesn't have any continuation. But what concerns the CD and the CC, they are defined independently of the 0 temperature, right? The CD at temperature, I define it as where the Monte Carlo equilibration time diverges. Where does the Boltzmann measure splits into exponentially many extremal Gibbs states? If you want, math stated in terms of mathematical physics. And this condensation temperature is defined in the way, when does the quenched free energy, that's the one you're interested in physically, start to differ from the annealed free energy? That's the definition of the decay, if you want. Okay, so these two definitions, they make perfect sense at finite temperature. You just talk about the Boltzmann measure, everything is a valid coloring, sure, but everything has its weight. And you just talk about the properties of the Boltzmann measure weighted by the energy, right? The temperature will just couple to the energy, to the number of links that are violated.
Higher temperature probably not.
Yeah, as the degree grows, these are growing, but for any average degree, if the temperature is high enough, you just have this paramagnet. So this, this just continues, but for every fixed C, you can find temperature high enough that you're above these things. So at infinite temperature, everything is trivial because it's just uniform measure over all possible Q to the n strings, and there is nothing particular about that. Yeah, that's right. Okay, so that's this. So maybe last comment, because before I somehow move more to the planted coloring, because I put this CS into the bracket, but this is also an interesting guy here. Although it's not interesting for the random graph coloring, because the equivalence between the random graphs and planted graphs breaks here. Okay, so whatever was true for the planted graphs, it's not relevant to the random graphs. So the last thing to wrap up about the random graphs before spending the rest of the lecture on the planted graphs is, what I promised at the beginning, and that was this. There was some comments about the algorithmic hardness, about what makes this phase algorithmically hard, really, right? So just to make the picture with the large Q. To tell you how these things scale with large Q. So actually the condensation and coloring both scale as Q log Q. Okay, so for three coloring it's kind of particular because CD is equal to C con and is also equal to the C stub. Okay, they're all equal for three coloring. But this is only for 3 colors. So somehow this phase is missing in 3 coloring, this one. But as soon as you have more than 3 colors, so I can write it here, that if Q is bigger than 3, then CD is strictly smaller than C condensation. Okay, this you don't see, you just have to run the numerical solution of these equations, right? Otherwise this is highly non-trivial claim, but that's what happens. And then at large Q, what happens is that actually the condensation and the colorability threshold, they go together. There is only a small gap between them. So at large Q, they somehow, this is really small. And this D, CD, that goes like Q log Q. So basically this region, that's this region where we have exponentially many clusters separated. Okay, so what does it mean about the hardness? So, so that equivalent definition of the CD is this property that the Monte Carlo equilibration time diverges there. So what does that mean? Well, that means that if you want to uniformly sample your space of solutions, well, then you will have a hard time because the equilibration time diverges, so you would have to need superlinear and probably exponential time to sample them. So sampling solutions surely gets hard at this CD. But sampling some measure is not the same thing as finding the ground state, right? Sampling over all colorings is not the same thing as finding one of them. And so, for instance, in the 3 coloring, whereas sampling indeed gets hard at average degree 4, we were saying yesterday that some algorithms work up to average degree that is maybe 4.5, 4.6 in terms of finding proper colorings. It's not uniformly sampled proper colorings, but they are proper colorings. In the large Q limit, sampling gets hard here. And we don't know of algorithms that would actually be able provably to find colorings inside this phase. But what really makes the algorithms stop here? So the thing is that we don't really know. Like we have one proposition that is better than just saying, is this dynamical glass transition? Because this clearly it's not. So one thing that we say could cause the hardness is related to this calculation we did yesterday about when a boundary implies the root, which in terms of BP fixed point means that at the fixed point, some of these guys are just delta functions on one color. Some of them, finite fraction of them, right? This, what it means in terms of the cluster, if you say, fixed point corresponds to the Gibbs measure, if, the fact that these probabilities are delta functions on one of the colors, that means that in the state that corresponds to that cluster, a finite fraction of nodes can take only one color. So there is kind of a backbone, like big fraction of nodes are actually fixed in that cluster, and the rest can somehow rearrange. But there is this frozen backbone of big part of the nodes, spins, actually cannot move. If they moved, you would have to jump to another cluster, but that's far away. That would take you exponential time or distance in terms of Monte Carlo steps. So, and there is, if once you find a solution, you have this kind of a way to check. You just run basically the belief propagation from it, and you see the fixed point that you reach from it. So you have a way to see if a configuration is in a frozen cluster or not. And it just so happens that all these algorithms that work really well up to almost the colorability threshold, they always find solutions that are not frozen. Okay, if you are on really small instance and you run many times, you can maybe find some frozen ones. But on big instances, this is really rare. And this is an observation where we were thinking about this question for several years, and this is the only thing that came consistently. So from that, we conjecture that it's really the frozen clusters that are hard to find. Okay, so we can compute these things, and from the computation we know that it's like a tiny region here close to the colorability threshold where all solutions are in frozen clusters. So this will be extremely hard to do some conclusive numerics about that because it's such a tiny, tiny region. In the large Q setting, where, well, experiments are, or numerics is hard to do anyway, because as soon as Q is bigger than 10, it gets, the connectivity gets very big and things get hard to do numerically. So a typical cluster gets frozen at the same scaling, Q log Q. That's the calculation that we did yesterday when we computed when is it true that with finite probability the root is implied. That is the computation that is telling us when a typical cluster gets frozen. And that was leading us to this Q log Q. So that's suggesting that maybe this freezing, is making things hard. But then actually that was kind of a more involved calculation that we did only last year with Guillaume Semerjan and collaborators from Turin, where we actually did kind of a more involved large deviation calculation, computing up to where there are some really rare, but some configurations that are not frozen. And I was expecting that we will see that all of them disappear here, but it's actually not what happens. So there are rare configurations that exist up to half that region, even at large Q. Well, so maybe there are some algorithms that could target them, or our conjecture about the freezing causing hardness is not true and there is something else that causes the hardness. So this we don't know yet. Okay, this is still an open question. So this is, so this is still an open question. Nevertheless, all this relation between what's happening in graph coloring and what's happening in these mean field models for structural classes, that just brought up all this picture of what's happening in the space of colorings that people in math and probability just had no idea happens. But once it was described in physics, they were really intrigued and understood what we are trying to say. And a lot of it, and in the last, say, 10, 15 years, a lot of it is like fully rigorous theorems like that these clusters indeed exist and bounds on the various phase transitions, and in some cases they have the phase transitions sharply, and there is really a lot of activity in rigorous probability proving or establishing rigorously this picture. That's, I think, everything I wanted to say about the random graph coloring. So random graph coloring is done for the purpose of this lecture, unless you have questions, and you're welcome to ask more questions in the afternoon. But let me spend what I have left, half, right? Okay, 42 minutes, great. About, going back to the planted coloring. So let's now completely, forget about the random coloring. Not completely, we will use what we learned. And let's talk about the planted coloring. So, okay, the way I introduced the planted coloring, it was extremely useful to somehow get a nice picture about what's happening in the random coloring. But we can actually interpret it very naturally. And to see, how natural and general problem it is, let me maybe generalize it slightly. And this generalization, I will call it stochastic block model. It's actually some people in sociology 40 years ago that called it this way, so that name sticked. So stochastic block model will be a generalization of the planted coloring, where again I start with a random configuration as star, but whereas before I was saying I just assign every color at random, here I say, okay, yeah, I do it at random, but the fraction of nodes that I assign in color A, so A is the index of colors from 1 to Q, is some NA, and these are some non-negative numbers that sum to 1. So I'm just saying here that the proportion of nodes that I assign to a given group is some generic fraction, right? It can be, 1/3, and then 1/10, and whatever is left to 1 if I have 3 groups, or, it's just some generic fraction, NA. And then I define this matrix CAB, and the CAB, okay, so how will I put the edges? So then I say that IJ is an edge with probability CAB divided by n, I always divide by the n to get in the limit of sparse graphs, if, okay, the S of, the color of I was A and the color of J in the start configuration was B. Right, so if I belongs to group A and J belongs to group B, then I connect them with probability CAB divided by n. Okay? So of course, if all these little NAs are equal, and if all these Cs are equal, then we are back with the Schwenny random graphs. If now, say, to have, so this would be a completely generic form, but one form that we analyzed kind of extensively was when all these are the same, and then the CAB is equal to some C in when A is equal to B, and is equal to some C out when A is not equal to B. And this would be precisely the graph coloring at finite temperature if C in is smaller than C out. And it would be exactly the planted coloring if C in is equal to 0. If I just don't put any edges between nodes that are in the same group. That was the planted coloring in the first place, right? So this is just a special case. So you see that both coloring, planted coloring are special cases of this stochastic block model. Okay, now why is this one somehow more intuitive? The way to motivate it when people talk about community detection in networks or clustering in networks, think of your high school and you were in some class and your friends were in other classes, and then you would be thinking about what is the graphs of friendship, what is the graph of friendships. So you're probably more likely friend with people from your class, not everybody, but on average people are have more friends in their class than in the other classes. So one could imagine just from observing the graph of friendships, one could somehow infer what are the divisions of the pupils in the classes, right? So that's an example for community detection. That's not a very maybe practically useful example, but another example could be that you have genes that are active when a person has a certain disease, and for certain groups of diseases, there are certain groups of genes that are active, and you would somehow like to cluster these genes according to the diseases to which, in which they play some role. And you could, imagine many other examples that, are more or less relevant to some practical scientific questions. So the stochastic block model is a very basic model for clustering, for network clustering that people in probability and math studied a lot because it's a great playground to actually say something about the properties of these statistical methods that we use for clustering. And planted graph coloring is just a special case of that. And so we could write the now I'm somehow really switching the heads and I'm going from the constraint satisfaction problem such as graph coloring to the inference problem, as Florent was talking about them, because what I'm really doing here is the graph. So this is defining the graph. The graph is an observation about some ground truth that I want to infer from the measurement. Right? This is, if I have the graph, the role of this S star basically is some structure that I have in the data that are represented by the graph. If I have some structure in the data, I would like to know about it because that's probably saying something about the world that created my data, so that will make me understand something about the world that created my data. Right? So I would like to know if that graph was just a random graph or if it was more likely a graph that was created in some way where the nodes were divided into groups and the probability that I observe an edge was related importantly related to in which group the nodes were in the first place. Right? So this is just a model for that. But that's a different kind of a problem. So here I would like to see what's the assignment of groups based on the graph, so the posterior distribution of that, which is again the normalization factor, and then product over all the nodes, and here the NSI, and then product over all the, and here I actually will write product over all pairs, and then the edge is there with probability that is CSI Sj divided by n if the edge was there. And that is 1 minus that divided by n if the edge was not there. Okay, so for the graph coloring, I was actually not considering this term because in the antiferromagnet it didn't really matter. But if now I go to the version where C out is bigger than C in, that's somehow what we have in mind at first when we think about communities, that we are more likely to be friends from our class than vice versa. But see, I don't know, if you are in your department and you are competing with the others for a promotion, then maybe you don't want to collaborate with them, you will rather collaborate with somebody else, so that will create kind of a disassortative structure. So what kind of structure is there, it really depends on the problem that you're looking at. So sometimes, in the assortative cases, this term is necessary here. Otherwise, everybody would just jump into same group, and that would be the guy dominating the posterior. So we have the posterior. We can again write the belief propagation for it. We can again run the bette free energy and do the same kind of analysis. So let's see what the type of things we can be seeing. Because yesterday Florent analyzed a related inference problem where we saw that we have two phases, that unless there is, okay, maybe it's a good point to put up the slide. I will show you one picture. I will just put it on and speak for 1 minute. That's what they told me it takes. How do I pull this down? Oh, it's also here, right? Oh, somebody's doing that for me. Great, thank you. Good, so when I wait 1 minute that it comes up. And so what I want to, our hammer, our method is the same, right? So we have this model. For the purpose of analysis, we know the S star. We have the belief propagation. We can evaluate our bette free energy. We can initialize the belief propagation in the planted configuration. C was the fixed point where it goes. And what does it mean for the inference problem? So we can have two kinds, in physics, we saw a phase transition here, right? So we have two kinds of phase transitions, basically, the second order one and the first order one. So yesterday you saw an example of a second order phase transition. So let me show you another example of a second order phase transition. This needs to wake up. Okay, that's it. So this is an example, and here I also actually have explicitly the comparison between BP and the Monte Carlo. So you can believe me that the points just lie on the curve, that I was not inventing it. Although the Monte Carlo has some considerable finite size effect, whereas the BP somehow doesn't, because it somehow half considers that you're already at infinity. So what is this? This is this stochastic block model with the probability to connect depending just on the fact if you are in the same or not group. So that's this C out divided by C in, right? So if it is 1, then it means that everybody is connected to only people. No, okay, sorry. So if it is 1, it means that C out is equal to C in. It means that the probability that I connect to people doesn't depend on the fact if I am in or not in the same group. So this is just the Erdős-Schwenyi random graph, okay? If epsilon is equal to 1. If on the other hand epsilon is equal to 0, it means that C out is 0 and C in is, everything else. So that means that I'm basically having disconnected groups. So if I observe a graph where I have, in this case, 4 disconnected groups, then it will be somehow easy to tell, right? So here it should be really easy. The overlap is probably very close to 1, and here it should be hard. And you see the same kind of behavior you saw yesterday in Florent's lecture, that, naively, unless for physicists it's natural, but if you're not in physics, you just expect some curve going from 1 to 0. But that's not what happens. There is a phase transition. So what it means here, this is an average degree 16 graph. So, why not? This is kind of a natural example. We have 4 groups, and everybody has on average 16 friends. That's reasonable. We maybe have on average 16, friends. Why not? And what this graph means is that, say that you are at 0.5 here. That means that the probability you are a friend with somebody outside from your group is half the probability that you are friend with somebody from your group. So you would say that's a lot of information, right? I have 16 friends, and I'm twice likely to be friend with somebody from my group. So this should somehow appear in the resulting graph, but it doesn't. The graph that this process generates is equivalent in the same way we were talking yesterday, contiguous, if you want to be mathematically precise, to a random graph. There is no way to tell if that graph is random or if it is created by the stochastic block model. The information is not there. It's information theoretically impossible to say anything about the ground truth configuration is S star. Okay? But if you increase that, you go from, say, half to 0.25, so you're 4 times more likely to be friend with somebody from your group than from outside. Then it's, you're better off. Then you can say, basically, for 95% of people, you assign them to the correct group. There are some outliers that have very few friends, for instance. This is 16 on average. So there will be somebody that have few friends, or there will be somebody that is socially different, that has more friends outside of their group than in their group. Why not? I mean, this is, we embrace differences, but that person, just from the graph, you will not be able to tell, right? These outliers you will not be able to tell, but there are only few of them. For most people, you will be fine. So this is what it means. And this is obviously a second order transition with everything that comes with it, right? When we first talk about this Ising phase transition, we plot the susceptibility, and we know that the susceptibility diverges around the critical point. So this is not the susceptibility, this is the belief propagation, this is the time belief propagation takes to converge. But you see it has the same behavior as the susceptibility. It also diverges around the phase transition. This is not surprising. This really is a phase transition with everything, with all the exponents and every criticality on all the things that we like in physics. Okay, but what about, so this was the assortative case, where you're more likely to befriend people from your group, and for a small number of colors. Actually, when either here the number of colors grows, or number of groups grows, or if you go to the disassortative case, and here I will just return this graph coloring, right, this is another case. Now you understand what this C-in means. That's just the stochastic block model, but saying that the probability to connect inside your group is 0, so this is effectively the planted coloring. What this is, or I should, let me put the free energy there as well. What this is a first order phase transition, right? The different fixed points of your equation, they appear discontinuously. And this is a kind of a mean field system, so you have these two spinodals where your, say, ferromagnetic, paramagnetic fixed point appears or disappears. And how do you decide which of them is the equilibrium one? Well, to decide that, you need to take their free energies and compare. The one with lower free energy is the correct one, right? As always in physics, we have two states. You compare free energies, the lower free energy, test the thermodynamic one. So that's what the red curve is saying, right? In this region is the paramagnet, that is the equilibrium one. And in this region, it is the ferromagnet, that is the equilibrium one. And now I can explain what this CS is. Where was it? Here. So let me erase the bracket. This is S for spinodal. So the spinodal of the first order phase transition, where the paramagnetic state disappears, that's where, even from random initialization, the belief propagation or the Monte Carlo starts to find something close to the S star. So that's where things, if you think in terms of inference, where you wanted to find back the S star, that's where the inference problem gets algorithmically tractable. You have an algorithm that gives you a right solution. But there is this intermediate phase. Where should I draw that? Maybe here. Everybody now has the network. No, come on. Or maybe it will. No, let me erase it. Everybody has the network. So now for the planted, or the stochastic block model, you can have cases where, as you're increasing some parameter, it doesn't have to be the average degree. Let me call it some, in general, like some signal to noise ratio. So not only you can have, so the more signal there is, the easier it is. So this is easy. Oh, I'm flipping it. Ah, you will, okay. You put noise. Let me put noise here, such that at least it's in the same direction as here. So as the more noise you have, so here it will be easy, here it will be hard, and here no, I'm sorry. I have it easy in this direction, so I was doing it right in the first place. So signal to noise ratio. Okay, so once again, so here it is impossible. When even the equilibrium solution is the paramagnet, then the inference is impossible. Even if you have exponentially costly algorithm and you compute the exact marginals, which are the bias optimal way to do the inference, you have no information. That means that information theoretically there is nothing. So it's IT impossible, Shannon impossible. It's not that you are sloppy about what you're doing. It's really impossible. Then you have this region where, I write easy, it doesn't mean that it's necessarily easy, but at least, if you're in these model situations and you have belief propagation, then you have an algorithm that is doing it for you, okay? So it's doable. So that's beyond this CS. This is before the CC. There is the CD somewhere here, but it doesn't play any particular role in the inference problems. And in the phase in between, it's hard. Physically, you're in this metastable state. And you cannot initialize close to the solution because you don't know what your solution is. That's what you're looking in the first place for, right? So unless you're doing some supervised learning where somebody tells you 50% of your correct labels, in that case, you can somehow initialize close to it. But if you're in the setting where you don't have any such strong prior information about, point by point what some of your nodes are, or some of the structure is, well, then all you can do is take your Monte Carlo, your belief propagation, or whatever, and initialize in randomly or uninformatively, right? Somehow, but not correlated with this S star. So you will just be doing whatever the blue curve here is doing. So in this phase, you will not be finding that there is good correlation. If you had exponential time and you could exhaustively search over all possible assignments of colors to nodes, and then you computed the true marginals of your posterior measure, that's fine. You would find the green curve up there. But unless you can do that with algorithms that we know of up to date, this region is hard. And here, it's kind of a sharply defined thing. Unlike in the planted coloring, where my conclusion was we have some better idea what makes things hard, but we still don't know really. I mean, here, I can, specifically for the stochastic block model, if I write a problem, find an algorithm, polynomial one, that does inference better than chance, so better than this. It does inference for 1 minus epsilon, where epsilon is some small positive number, CS. Now, if you find such an algorithm, well, then you will become really famous, I think, because this is a formidable open problems. In these, these are basically benchmarks for really hard inference problems. And they arise because physically you are stuck in a metastable state of a first order phase transition. And you could think somehow first thing, okay, what if I change my Hamiltonian? What if I change my landscape? Maybe the spinol will change a little bit. So, when people do algorithms, actually, it's not, people in computer science, they don't think only of belief propagation, Monte Carlo, variational mean field. That's very limited kind of a view. They do all kinds of things. They do, for instance, a class of algorithms that is considered very powerful and very popular are the semi-definite programming relaxations of the problems. And these algorithms, basically what they do is they say, my spins were discrete, and that's kind of a nasty space to optimize above. So what if I take that my spins are some generic dimension D vectors, continuous ones, and now I tried to optimize over that space, and of course then I somehow have to project back into my original space, but what if I try that? Will it help, right? And in many situations these things help, and these SDP relaxations are very popular, but in cases like that, it does not help. You know, even doing crazy things like going to different spaces, projecting to different things, going to different classes of algorithms, nobody has an algorithm that would beat, you know, this is a well-defined number. I can write the number. Yeah, why don't I write the number, right? I should write the number. So that's actually, then so where is my number? So we computed that number. What's that CS, right? Let me see. Here is it. So when we computed this stability in the second lecture, that for the coloring was Q minus 1 squared, that's where the paramagnet is not a stable fixed point anymore. That's the same thing here. That's the same point that we are interested in, right? So in the planted coloring, this CS is just this Q minus 1 squared. Now, in the generic stochastic block model, this actually happens. So I should say, where is my stochastic block model? Now this I can erase it. So in the generic stochastic block model, actually, this paramagnetic phase where really I have no detection, you know, it exists under some condition. So what needs to be true, I should have maybe written that before, is that sum over CAB and B is some, you know, CA, B from 1 to Q is some CA, which is basically the average degree of group A. If different groups have different average degrees, then by histogramming the degrees, I have some information, right? So this is somehow the simpler case. If the CAs are different, that's a simpler case to do inference. So we will be, so these figures that I showed, you know, by the way the parameters are chosen, because I just choose the C in, C out, and all the groups the same size, is that the average degree of every group is the same. So under this condition, which is the particularly challenging case, I can, you know, I could repeat this stability calculation, and I would be, you know, doing, you know, I will just write this equation that we already got, and it would be the same in this case. So sum over B, T, AB. Maybe I called it RS the other day, but now it is AB. So you see we did this. So we would have a fixed point of the belief propagation, which now would be the uniform fixed point would be, this is just equal to NS, which before was just 1 over Q. Then we linearize around this fixed point, and the linearization would lead us to this equation, where this TAB matrix, we computed it, that was just the matrix of the derivatives evaluated at the fixed point. And for the generic stochastic block model, this TAB is just equal to this. So it's some little Q by Q matrix, and then the stability condition is again the average degree times the largest eigenvalue square is equal to 1. And it evaluates to something really simple. In this case, we just have C in, C out, and all the groups have the same size. And this is, I will just write this expression, because it's somehow, you know, it's something that we derived, I never remember, that we derived 5 years ago now, but, you know, it was not known before, and it created some buzz in the math community where people try to prove that something is indeed happening at this place in the stochastic block model. So this is saying that the problem gets easy if the absolute value between this difference is bigger than number of colors square root of the average degree, right? It's a quite simpler expression that defines the average degree where the problem becomes easy. So I write that, and in the last 16 minutes, good, a lot of time, so now, okay, what else? So let me just think if there was something else about the inference problem that I wanted absolutely to tell you about. Maybe not. So maybe some questions about the stochastic block model as an inference problem, where, you know, you have this, sometimes you don't have this hard phase, but sometimes you do have it. And when you do have it, it's like a formidable puzzle for people in inference and compute and algorithms. right? The thing is that here, and I was a little hesitant when I wrote easy here, right? Because it's easy if you have the belief propagation. But doing optimal inference in the stochastic block model, it's actually not something that people like knew how to or know how to do optimally without the belief propagation. Okay, and there is no rigorous proof yet that the belief propagation really is optimal, that it really converges to the optimum and things like that. So there are still open questions related to that. But not so much, right? Not so much. That's a good question. Yeah, maybe something that I wanted to comment about. Like here, the hard phase was there because of this freezing and this dynamical replica symmetry breaking, this like horrible ergodicity breaking that happens in that phase space that is, really interesting mathematically, and algorithmically it's making things hard. Here, somehow physically the system is much simpler. This is really a transition from a ferromagnet to a paramagnet. It's a first order phase transition. So you are stuck metastably in the paramagnet if you start in the paramagnet, right? There is no glass here. Actually, that's a nice property about this. Flora mentioned it yesterday as well. You can actually prove that if you are doing bias optimal inference, it means you define your model and hence you know what's the right prior and you know what's the right posterior. Then replica symmetry breaking cannot happen. This static replica symmetry breaking cannot happen. Like either you are paramagnet or you are ferromagnet. You cannot have this non-self-averaging of the overlap. This you can prove directly that cannot happen. And we don't know of anything else that goes wrong in these kind of mean field-ish geometries. So these, and we now have, in some settings, under some conditions, we have proofs that this is indeed true. So this is solid. So there is no glass here. So this hardness is a different kind of hardness.
The overlap is zero at that.
The overlap is zero. Yes, the overlap is zero, and you're stuck there. And one could think that there could be some way around, but finding that way around is an open question. If you can or not, or it will be hard to prove that you cannot, because on the way you would prove that P is not NP, right? That's the same stories. But proving that for some class of algorithms you cannot, or finding some country examples, that may exist. And that's, a lot of people are looking at this question, in our community in statistical physics, but also in statistics, in probability, in computer science, machine learning. Several of, because this is one problem where this hard phase appears, but you will see one in Florent's lecture after the tea break, and the most famous one in math maybe is the blunted clique problem. In error correcting codes, before people started twiggling with the graph in low density parity check codes and doing what they call spatial coupling, they also had this threshold beyond which the belief propagation decoding was not working and they had no idea what to do with it. So they're in a lucky situation. They can change the graph. So I don't know if Florent will get to what to do in that case. But here we cannot change the graph that's given to us. But there are other problems. So the compressed sensing Florent will mention, or things like sparse PCA, things in machine learning, like in perceptron learning, neural networks learning. All these problems, you can set them in some kind of a spin glass way and compute these phase transitions, and you find this thing. In the same way as if you study phase transitions in physics, and you go after first order phase transitions, you do find them everywhere. You just change a little bit your parameters, your interactions, and there are always some regions where things become first order phase transitions. And that's what corresponds in inference to the hard phases. It's kind of a established picture, but understanding it more mathematically is something open and kind of exciting. Okay, so 16 minutes reduced to 11. So let me tell you about, yes, other questions.
Hard phase is then probably related to your belief propagation model. If you came up with another model, it may not exist as a hard phase, right?
So I agree partially, but distinguish between belief propagation and the model, right? The model is one thing. The model here is the stochastic block model, and that's in no way related to belief propagation. Belief propagation is the method I use to analyze this model. I could analyze it in other methods. It's just my limitation that that's the method that I have. But maybe 10 years from now, we will develop new methods in probability, and we will have other methods to say what's happening in this model. So yes, it is specific to this model. But it is not specific to the belief propagation. If you analyze it with Monte Carlo, if you analyze it, any other way that to analyze the posterior distribution of that model, you will get the same phase diagram because this is the exact phase diagram. Belief propagation does describe the exact phase diagram. Now, if you start changing the model, of course, you will have a different posterior distribution. So, of course, you may have different phase diagram, right? It's like changing the Hamiltonian. So, of course, generically things will change. But then, and also, if you are given a data, then it's important, and many people are studying and spending their career studying the question, like, what is the good model for the data, right? So here I'm rather in the really basic research case where I just, I have my Ising model, and I study. It's not an Ising model, but you see, it's my simple model. And I study what are, the options, what are the things that I can see, what are the possibilities. And then, if I see behavior like that in that model, and as physicists, we somehow believe in universality, which doesn't mean that we believe this always happens. But it does mean that we believe if it happens in this model, there must be other models where it also happens, right? Not in all of them, because we are not naive. But in some of them, it will be relevant. So that's somehow the philosophy. Okay, but let me tell you about, so Pavel was actually asking me about the Laplacian and the spectral methods after my first lecture. So that's, if you are, also for physicists, this is something very natural, but if you are somebody, I could have asked you that, like when I define the stochastic block model, can you think of some algorithms to actually find these clusters, right? If you're somehow see the probability of connecting, if you're in the regime where the problem is very easy, right, somewhere here, right, many algorithms will work. So probably you're all smart people. So far in that regime, probably you will not need more than 10 minutes to think of some very reasonable algorithm that will work, because kind of many reasonable things will work. And one of the first things that probably many of you would think about, but definitely almost everybody in, say, statistics and machine learning would think about is spectral methods, right? I created a graph, so the data is presented to you in terms of a matrix. It's a very sparse matrix, but it's still a matrix, right? So why don't you look at its spectra and at the eigenvectors? And won't your eigenvectors be related in some simple way to this configuration S star? Right? So let's think about it as physicists. So let's think, this adjacency matrix, if you power iterate it, it's almost like doing a random walk. It's not quite random walk, but almost like random walk on the graph. And we know what the random walks are doing, right? So what's the equilibrium solution of a random walk? Well, it will walk on the graph and it will visit every node with a probability that is exactly proportional to its degree. So that's the leading eigenvector of the random walk matrix. It's just the degree, it's just the vector of degrees. And that's it, okay? What will be, so now you study dynamical systems, now I will ask you, how long will it take to the random walk to get to this equilibrium? And so if you studied properly your dynamical systems, what you should immediately think about is, okay, I should look at the second eigenvalue, and the gap it has from the first eigenvalue, that will be the typical time that will be describing the convergence of my Monte Carlo Markov chain to its equilibrium, right? This we learned about. And so this is when you look at the eigengap. But what now if you look at the eigenvector corresponding to the second eigenvalue? That will be describing the slowest mode, the slowest non-equilibrium mode in your system, right? And if you have a graph that is created from two groups that are quite separated, what is the slowest mode? Well, that's that the random walk will just stay for a long time in one of the groups, then it will jump to the other one, then it will stay a long time in the other one, and it will be doing like that, right? So the slowest mode the eigenvector of the second eigenvalue will just be strongly correlated to the groups. It will have, for instance, large positive elements on one of the groups and large negative elements on the other group. That's how it will look like. This is physically very natural. So the eigenvectors, they do contain information about the groups. So this is example from random walks and dynamics in physical systems. But when people in data science talk about dimensionality reduction, the first method you learn about is the principal component analysis. What's principal component analysis doing is taking your data matrix, so the adjacency matrix in our case, it's computing the first, it may not be symmetric matrix, so singular value, but our matrix is symmetric, so let's reduce to symmetric matrices. So in that case, you compute the first eigenvalues, and its eigenvectors are the principal components. That's the directions in which your data vary the most. That's the directions that you should try to keep if you want to describe the structure of your data. So PCA, is another example of a spectral method. So spectral methods where you just look at leading eigenvalues and corresponding eigenvectors of the matrix are very, broadly used and useful methods for inference. Now, we were working with sparse graphs. A lot of the guys here are zero. There is a universal trouble with spectral methods for sparse graphs. That's the following thing. Think back about the random walk, okay? And now, what's bad with sparse graphs? Sparse graphs have big heterogeneity in the degrees, right? Something like an Erdős-Fényi random graph can have average degree 5, but the highest degree node will have degree log n. Okay, that's just what happens. If you choose random elements from some probability distribution that is not bounded, the highest element will be log n. That's a generic, extreme value statistic result, right? So log n, so it's very big. If n is big, it's very big. And now what happens with eigenvalues on a matrix that has this kind of a heterogeneity, that some of the rows or columns have very big average value? Think about, again, the random walk. What will the random walk do? Well, if it starts at that high degree node, first it goes out, right? And then, with some probability that is related to the degree of the node outside, it goes back. And when you count the overall probability that it goes back, you realize that having a node of large degree creates an eigenvalue that is of value square root of the degree. So if it is log n, square root of log n is still big, right? So any kind of eigenvalue that you had that was big 1 because it was describing the structure in the stochastic block model or something like that, it will just get, for really large graphs, it will get overcome by these square roots of log n, okay? So this we know from physics as well. We call this the Lifshitz tails in the theory of random matrices. And in condensed matter theory, when we talk about localization and when we call about impurity states, that's exactly these kinds of eigenvalues and eigenvectors that are localized to these high degree nodes. And this is an example for the random walk matrix, but you can take different matrices, say the Laplacian, which is another popular matrix to do spectral methods on. And this one as well, as long as the graph is sparse, it will have some the dominant eigenvalues will have some eigenvectors that are localized on some uninteresting parts of the graph. It will not be related to the global structure as star that we are looking for. So spectral methods are not universally so good for sparse graphs. Notably, they don't work down to this phase transition CS. So I have a picture to show you that. So this is a picture. This is still for the stochastic block model. Now here I put the C and minus C out. And the black curve, that's the BP. That's the belief propagation, okay? That's the best we can do. Model of the fact that you have to prove it, but if, that's what the bias optimal inference is doing. And now these all other curves, that's the result of the spectral methods that people commonly consider in statistics and machine learning. That would be based on the random walk matrix, based on the adjacency matrix, based on the Laplacian, normalized in various ways as people do it in machine learning, on the modularity matrix, which is a popular matrix for the community detection introduced by Newman, And I think that's my examples. And then there is this matrix B. And that's the blue points. And you see that the blue points are doing considerably better than all the other ones. And how comes? And what's this matrix B? So I just have 26 seconds left, so that's good because I don't have time to write it, which is good because it's already written. This, you can write it as you can write that epsilon is an outer product of some matrix B related to the graph times this matrix T times epsilon, right? So this would be like T plus 1, T, if you are power iterating your matrix. Oof, okay, good that I'm done. So this T is some little Q by Q matrix that we don't care about much, but this B is this, message passing matrix defined here. We call it the non-backtracking matrix. And it does much better than the other ones. It doesn't have this trouble with the leading eigenvalues being localized on some uninteresting parts because it's not backtracking. It's just, it's a trivial fact, you forbid the backtracking so you don't go back to these parts where otherwise you would localize. You go somewhere else, you discover the global structure. It's a simple thing. And this equation, I was telling you yesterday, it was sitting there in the works of Thouless since '86 and in many other works since then where people analyze this stability for 30 years. And people in machine learning and statistics were using spectral methods and scratching their head how to do better spectral methods for sparse graphs for at least as long time. And until 2013, when we suggested, why don't you try that matrix? Nobody somehow thought about that, like put these things together. And that's somehow the, great last minus 130 minutes message of my lecture, is that basically this field that I tried to present to you and we tried to present to you in these lectures is basically about taking the calculations that we had in physics for a long time, like this Thouless calculation of the stability, and translating them into the algorithmic world and seeing where we can find some matches which lead to something nice. And let me just show you the spectrum of that matrix because it's kind of beautiful. It's a non-symmetric matrix, so it has a complex spectrum. That's how it looks like. Okay, we could also talk largely about that matrix. And this is also, this would be on the stochastic block model, how the spectrum looks like. This would be on some of the real graphs. Well, I can show you that later. Okay, and since somehow we realized that this is a good matrix to base spectral methods on, this is not the only application where you can do that, because as I said, spectral methods are universally useful. So since then, people came with maybe several dozens of applications for this kind of an algorithm. So, okay, minus I don't know how many minutes because you closed it, so I'm stopping here.